All right. Good morning, everyone. I guess we'll get started. So you guys probably know that we are going to be online for 1 week, but the lab will still meet in person. Okay. So just a reminder that we will still meet in lab in person for this week. And then also the next homework is up online, I believe, and it's due on the 27th. Okay. So I think that's next Tuesday, if I'm not mistaken. Um, so because there's a lot of active cases in the community, so for the lab section, I will encourage you guys to bring your face shield. Okay, so um, for the time that you are doing the lab together, if you are face to face, not separate by the plexiglass, then you want to put on your face shield. Okay, so bring your face shield to the lab. All right. Now, starting from this week, for the lab, we will need to use a software called Pascal Capstone. Okay, so something look like this once you install. So here is a link where you can download the software. So I will encourage you guys to do this before you come to the lab. So click on the link here. It will direct you to the web page where you will be find the downloads for the either Windows machine or Mac machine. So just download the free trial, okay, and then install it. So once you install it, then you can run it after you install it. So the first time you run the software, it's going to ask you either buy the license or enter the license key. So we have a site license over here. You guys can use this site license, okay? So if you install it, the first time you run, you can put in this license key numbers, okay? Now make sure, so this like big zero, this big look like big O's, they are zeros, and then small O's, they are O's, okay? So they are lowercase O's, okay? Otherwise, I think you guys should be able to read the license key here. All right, so that's for the lab part, okay? We will get started with the lecture of the day. So again, we'll just start with what we learned last time. So last time we learned about linear momentum. So the definition of it is linear momentum in the symbol P. Note that it's a vector, so we put the arrow on top of it. That's equal to mass times the velocity. Velocity is also a vector. So momentum or linear momentum should have the same direction as the velocity, okay? The SI unit is kilogram times meters per second. And from Newton's second law, we mentioned this. So we are more familiar with this expression, net force equal to mass times acceleration, okay? But in the original theory that Newton proposed, he actually said that net force should be equal to change in momentum divided by change in time t, okay? So in most cases, the mass is not changing. So then you will use the first equation. But in some scenario, as I mentioned last time, for example, the rocket launching, in that case, the mass is changing. So then that will also give you the force there, okay? And we also talk about impulse. Impulse is defined as the force on the object times the time t, the impact time, okay? So delta t. Impulse is also a vector because force is a vector, okay? Time is a scalar, force is a vector, so the multiplication of it should be still a vector. The SI unit for impulse is newtons times meter, and that's equivalent to kilograms times meters per second. And we'll see that in the impulse momentum theory, okay? So impulse momentum theorem basically says the impulse, okay, that is being added to an object that is equal to its momentum change. So delta p, I equal to delta p, it's the impulse and momentum theory. And then you can figure out like I by doing F average times delta t, delta p will be equal to mass times delta v, okay? All right. So again, looking at the Newton's second law in the original form, net force equal to delta P over delta T. If net force is equal to 0, then delta P will be equal to 0. That means delta P is not changing. So once if the quantity is not changing, then we say that quantity is conserved. Okay, so similar like what we learned when we have the kinetic energy energy conservation. So that means your final momentum is going to be equal to your initial momentum. Okay. Now, if you have a system of several objects, then if the external forces add up to be zero, then internal forces will cancel out each other, so the momentum will be conserved. Okay. In that case, the summation of the momenta from each of the object will be equal. Final will be equal to initial. Okay. But for individual object, their momentum might be changing. Okay, just keep that in mind. And in most of the cases, they are changing. Okay, but the summation of momenta from all the objects will remain the same. All right. So I think we looked at one example last time. So we are going to I'm going to just give you guys a practice problem to start with here. Okay. So this one says a 1.80 kilogram falcon catches a 0.650 kilogram dove from behind in midair. What's their velocity after impact if the falcon's velocity is initially 28.0 meters per second and the dove's velocity is 7.00 meters per second, and they are in the same direction? So this is one-dimensional motion. There's a falcon in behind and then there's a dove in front, and they each have initial velocity, but after the impact the two stick together. So what would be their final velocity? Okay, so you can treat the two as one system and then apply conservation of momentum. Okay, so I'll give you guys a few minutes, and then once you have your answer, you can click on the problem to submit your answers online. Okay. All right, I think I see some responses in there. We can take a look at the solution together, but you can still submitting your response if you want. Okay, so the falcon is behind the dove here, that in one-dimensional motion. Okay, so V1 for the falcon is to the right, and V2 for the dove is also to the right. Okay, so you can put them all both in the to the left, so it doesn't matter. Okay, um, we are given M1, M2, right? So we can write that because there's collision between the two, or there's impact of these two. So these two collide together. If you treat them as one system, then there's no external forces here. So then you can actually apply conservation momentum for the system of the two birds, okay? So you'll be doing like P final equal to P initial, okay? And then P final, because they are together after the impact, okay? Because the falcon caught the dove. So then you'll be doing the combine of the mass, the two masses, okay? And then multiply by the V, their common velocity, okay? Because they are together, then equals to initial momentum of the two. So m1 v1 plus m2 v2. Okay, so this is the final velocity for the two together, and then this is initial velocity of the two. Now you do m1 v1 gives you the initial momentum of falcon and the initial momentum of the dove. Okay, you are looking for this guy, so you can set up that v then is equal to um, should be equal to m1 v1 plus m2 v2, right? Divided by m1 plus m2, okay? You have everything you needed. You just need to plug in the numbers here. So 1.80 kilograms times v1, 28.0 meters per second, okay? Plus 0.650 kilograms times 7.00 meters per second, and then divided by the summation of the two masses, right? And then so when you put into the calculator, you should put like a extra parenthesis on the top and an extra parenthesis at the bottom. Okay, so so that will give you 22.4 meters per second for the final speed of the two when they are together. Okay, any questions you guys might have? All right. I think I see a couple of responses with the correct answer there, so that's very good. Okay, um, so if you guys are clear with this one, we'll move on. All right. So next we'll talk about types of collisions. So basically, there are two main types of collisions. Okay. So one is called the elastic collision on the third line here, third item here. The other is called the inelastic collision. Okay. So for an elastic collision, the momentum is conserved, but also at the same time the kinetic energy is also conserved. So elastic refers to the kinetic energy is conserved. Okay. Inelastic collision, that means only momentum is conserved, but kinetic energy is not conserved. Now, for collision, it's defined as when you have two objects striking one another, or maybe sometimes you have more than two objects, okay, involved in a collision. So two or more objects striking one another. Now, unless otherwise specified, so we will consider time of collision to be short enough that external forces might be ignored. Okay, so for example, for the example we just checked, for the two birds collide together. Okay, so there might be air resistance that's doing the giving the system for the impulse at that time, but we will assume that because time is short enough, so then we'll ignore that. Okay, so then whenever you see a problem that says collision, if otherwise specified and any other conditions, then you will assume that you can apply conservation of momentum because you will ignore all the external forces. Okay, all right. So then for there are two main types of collision: elastic collision and inelastic collision, as I mentioned. Now, for inelastic collision, there's a special cases when you have the two objects stick together after the impact. So then in that case, the loss of the kinetic energy would be most. Okay, so then it's called completely inelastic collision. So when you see the word completely inelastic collision, that means the two objects stick together after the collision. Okay. All right. So we'll take a look on those two types of collisions one by one. Elastic collision and inelastic collision. Okay, so and we'll just focus on one dimensional. Now, for two dimensional, you can expand that into the second dimension, but that's something you can we will talk about later on. Okay, but for right now, we'll just focus on one dimensional. Okay, so let's take a look for elastic collision. As I mentioned, so when you see collision, that means you can first apply conservation of momentum. And then when you see the word elastic collision, that means you can also apply kinetic and conservation. So if you have two objects, okay, like the figure indicates here, one strike another, and then if it's a elastic collision, so you can write out two equations. The first one is the conservation of momentum. So V1 and V2 are the initial velocities. V1 prime, V2 prime are the final velocities. Okay. So then for conservation of momentum, you can do the initial momentum, the sum of initial momentum of the two, that is equal to the sum of final momentum of the two. All right. So that's conservation of momentum, the first equation. And then the second equation, you can write the kinetic energy, the sum of kinetic energy of the two initial, that should be equal to the sum of kinetic energy final of the two. Okay, kinetic energy is equal to 1/2 mv squared. All right. So if you are given the masses, if you are given the initial velocities, you should be able to figure out the final velocities of the two by using these two equations, because now you're looking for two unknowns, you have two equations to use. Okay. We will take a look on one example here. So this one says, it says a 732 kilogram car stopped at the intersection is rear-ended by a 1720 kilogram truck moving with a speed of 15.5 meters per second. If the car was in neutral and its brakes were off, so that the collision is approximately elastic. So we're going to treat this as an elastic collision. Okay, satisfying the final speed of both vehicles after the collision. Okay, so this is an elastic collision problem. So let's see how we can solve for this one. Okay. So as I mentioned, we can write the two equations: conservation of momentum. So m1 v1 plus m2 v2 equals to, this is initial momentum, and then m1 v1 prime plus m2 v2 prime. Okay. And then the second equation you can write is 1/2 m1 v1 squared plus 1/2 m2 v2 squared equals to 1/2 m1 v1 prime squared. Okay, so this is v1 prime plus 1/2 m2 v2 prime and square. Okay, so you have two equations, and we are given that m1 is equal to 732 kilogram, and then v1 is equal to 0 because it's initially at rest. M2 is equal to 1720 kilograms, and then V2 is equal to 15.5 meters per second. We are looking for V1 prime and the V2 prime. Okay. So we have two equations, and with two unknowns, we should be able to solve for the two unknowns. Okay. Now, because this is there's squares involved here, so that means the unknowns has squared, right? So that means this is quadratic formula. Now, normally you should be able to do it for just one, right? If you have one unknown and then it's in quadratic form, you should be able to solve for it, right? But in this case, it's a little bit complicated. You have two unknowns, they are in squares, okay? And then you have two equations. But basically, you will be following the same rule. You can replace you can write one unknown in terms of the other unknown from one equation. Okay, so you'll be looking at the first equation, and then in the second equation, you are going to replace that unknown, okay, with the expression of the other unknown, and then so then in the second equation, you only have the other unknown. Okay, so let's take a look here. But before we are doing anything, let's take a look, because v1 is 0, so that means this term will be 0 and this term will be 0. Okay, so this term will go away, this term will go away. Okay, so that probably will make our life a little bit easier. Okay, but let's take a look here right now. Now this equation here, let's put the numbers in here. It's going to be M2 is 1720, right? So I'm going to just leave out the units for right now, because I know everything is in SI unit for here. So then my final answer should be also in SI unit. Okay, so 1720 for M2 times V2 15.5 equals to M1 will be 732 V1 prime plus 1720 M2 V2 prime. Okay, and then the second equation will be 1/2 1720 times 15.5 squared equals to 1/2 732 times V1 prime squared plus 1/2 1720 times V2 prime square. Okay, so now these are your two equations. Okay. All right. So you can calculate for the numbers, right? So put these two together into the your calculator. All right. So it's going to be these two. It's going to give you, and this equation becomes 26660. Okay, for that equals to 732 v1 prime plus 720 v2 prime. Okay, and then this one, it's going to be 206615 equals to 1/2 of that guy. You can put that into calculator, see what number that gives. V1 prime square plus that would be 860 V2 prime square. Okay, so now your two equations becomes this. From here, you can write V2 prime in terms of V1 prime. Okay, so basically, you are going to move this guy to the other side of the equation first, right? Leaving this term on the right hand side, and then divide both sides of the equation by 1720 to give you v2 prime. So that would be 1720 at the bottom here. On the top, you will have 26660 minus 732 v1 prime. Okay, and then you are going to replace. Let me stop sharing so you might be seeing larger view. So then you'll be replacing this here in the second equation with this expression. Okay, so take this expression here. All right. So then your second equation becomes 206615 equals to 376 v1 prime square plus 860 times this expression 1720 at the bottom 2660 or 6660 minus 732 v1 prime, okay, and then square. Okay, so don't forget about the square there. All right, so then this is 376 v1 prime square plus, okay, over here for the top here, okay, it's going to be 26660 square. So this is a minus b square, right? Then it will be a square minus 2 times 26660 times a times b, okay, v1 prime plus 732 v1 prime square, okay. At the bottom here, you'll be having like 1720 square, right, times 1720. And then there's 860 in front. So 860 is exactly half of that guy. So this becomes 2 here. Okay, 2 times 1720 there. All right. Now I think we are getting there. So this is going to be a quadratic formula with the V1 prime as the unknown, right? All right, so you can move this to this side of the equation, okay? So then it becomes 0 equals to whatever here we have, 376 V1 prime square plus, okay? I'm going to just move this guy first in front, so then the two you can combine the two, okay? So this is going to be 2 times 1720, and the bottom here on the top you should have 732 squared, right? And then V1 prime squared, okay? So then you can combine these two together because they are V1 prime squares, okay? And then minus the second one, I'm going to take this one here, minus, so we should have 2 times 1720 again here, 2 times 26660, 732 V1 prime, okay? A little bit tedious here, but if you are careful, you should get to the right answer. So the 2 and 2 will cancel out, okay? Now the constant term plus 26660 square divided by 2 times 1720. And then don't forget about that term, we move to the other side of the equation, okay? So minus 206615, all right? Okay. So now if you do this, combine these two together, so 376 plus 732 square divided by 2 times 1720, right? Times V1 prime square, okay? And then the rest should remain, the rest 3 terms, okay? So if you put these numbers into your calculator, it will give you a number which should be 531.76, okay? V1 prime to the square. Now minus, okay? Yeah, minus the second term, which is coming from here, okay? So it's coming from here down here, minus 11346 V1 prime, okay? And then plus these two constant terms, you want to combine them, okay, together. And then if you put the numbers in your calculator, you'll figure that this actually cancel out, okay? So plus 0 at the end, okay? All right. So then it's 0 over here. So this one minus that one goes to 0. So basically, yeah, it seems to be like a quadratic formula, but actually not quite because the constant term is 0. Okay, so then actually it's not. So actually, this guy minus that guy is equal to 0. So that means 533.76 V1 prime square is equal to 11346 V1 prime. Okay. So you have V1 prime square on one side, V1 prime on the other side. So they will cancel out the square. Okay, so this guy goes away. So at the end, your V1 prime is going to be equal to 11346 divided by 531.76. Okay, that's going to be 21.3 roughly meters per second. Okay, so I'll put the unit at the end. Okay. And then once you have your V1 prime, you'll go back to here where you have V2 prime in terms of V1 prime. Okay, so just replace V1 prime with 21.3. Okay, then you'll be solving for your V2. So V2 will be 6.42 meters per second. Okay, so then you have solved V1 prime and V2 prime. Okay. So I think the algebra is a little bit tedious, but it's kind of straightforward. You should be able to follow step by step. Okay. So as I mentioned, first you write out the conservation of momentum and then conservation of mechanical energy. Okay, and then from two equations you solve for two unknowns. Okay. So let me pause for a few seconds if to see if you have any questions. All right, so if that's clear, we will then take a look on the inelastic collisions in one dimensional, okay? So for inelastic collisions, so then one object strike another object, but in this time, the kinetic energy is not conserved. So you can only apply for conservation of momentum, okay? You cannot apply for the other formula, the conservation of kinetic energy there, okay? So let's take a look again, one example here. So this one says an air track cart with mass of m1 given, and then speed of v0, 0.85, collides with and sticks to the second cart that is at rest initially. If the mass of the second car is m2 equals to 0.44 kilogram, how much kinetic energy is lost as a result of the collision? All right, so now you have one car strike on the second car. So this is likely what you are going to do next week for the lab on collisions and momentum. Okay, so this V2, this guy is initially at rest, not moving. And then M2 is going to be 0.44 kilogram. Okay, you can put a weight. You probably got like two identical cards, but you can put a weight on top to increase the mass. And then this guy, M1 is 0.32 kilogram. V0 is 0.85 meters per second. Okay, after the collision, they stick together. Okay, so after the collision, one car stick with the other car. Okay, so then it's asking what would be the kinetic energy lost. All right. I think when we talk about change in kinetic energy, we know that you are doing final minus initial, right? Now for a lost of certain quantity, okay? So that means the initial minus the final, okay? So if you are looking for the loss of certain quantity, it's actually the initial minus the final. So like when you are doing business stuff, right? If you are doing business, then your initial capital minus your final capital. If it's a loss, your initial capital should be more than the final capital, right? Then the difference will give you the loss. So initial minus final, okay? So K last or KE last should be equal to KE initial minus KE final. Okay, that's what you are looking for. All right, and then because it's an inelastic collision, because they stick together, so in that case, the loss of kinetic energy will be maximum. Okay, so then you can only apply conservation of momentum. So P initial equal to P final, or P final equal to P initial for the system of the two. Okay. I think I'm going to give you guys a few minutes to see if you can solve for this one. Okay, so just maybe 2 or 3 minutes for you to get started, and then we can probably look at this together. Okay. All right, I think you guys probably have some kind of idea on how to solve for this, okay, but we'll take a look here together. So as I mentioned, you can apply conservation of momentum here. So P initial should be equal to P final. Initially, you should add the momentum of the two up, okay, so M1 V0, all right, M1 V0, and then plus the momentum for the second one. It's at rest initially, so this one doesn't have any momentum initially, okay, zero momentum. So then that's it for PI. P final, the two stick together, they will share a velocity v, but their masses are combined. Okay, so m1 plus m2. Okay, v. So you are given the masses, you are given v0, so you should be able to solve for the p final of the two combined. Okay, so then similar to uh, the first problem we saw earlier. So then this would be v should be equal to mv0. You divide both sides by m1 plus m2 basically. Okay. So then this is equal to 0.32 m1 times 0.85 v0 divided by 0.32 plus 0.44. That gives you 0.358 meters per second as the final velocity of the two together. Okay. Now you're looking for kinetic energy lost. You are doing KEI minus KE final. Okay, so KE lost is equal to so initial 1/2 m1 v0 square, right? Plus this is m1 for m1 plus the second one will be 1/2 m2 0 square, right? Because m2 is initially at rest. Okay, so that guy goes away. That's going to be 0. Now minus the two stick together, you can put them together. So 1/2 m1 plus m2 v square. Okay, you have everything you need, I think. So you're going to just plug in the numbers. So this would be 1/2 0.32 kilogram times 0.85 meters per second square minus 1/2 0.32 kilogram plus 0.44 kilogram. Okay, and then times 0.358 meters per second square. Okay, so put everything into your calculator. It's going to give you 0.0678 in joules, or roughly 0.068 joules. Okay. All right. Questions you guys might have? Okay. There's one response not quite right. You can check on the numbers. Okay. So if you guys are clear, we are going to take a look a final example here for today. So this one is the integrated concept. Okay, so it's basically collision and then the energy conservation. Okay, so it says 0.454 kilogram block is attached to a horizontal spring. Okay, so that's like 1 pound. And the spring is at its initial equilibrium length. The force constant of the spring is 24.0 meters newtons per meter. The block rests on a frictionless surface. 0.0454 kilogram watt of putty is thrown horizontally at the block, hitting it with a speed of 8.80 meters per second and sticking. What's the maximum compression of the spring by the putty block system? So let's see it here. Let's draw a sketch here to represent the problem. Okay, so initially, so there's a spring in equilibrium. Okay, now there's a block attached to it. which happens to be 1 pound or 0.454 kilogram. I'm going to call this capital M because this is a larger mass. And I'm going to say the party here has been thrown. This is the small m. Okay, so this guy has been thrown in that direction towards that. And that's 0.054454 kilogram. V0 of that party is given as 8.8 meters per second. Okay, so then there's collision between the two, the small mass and the big mass. Okay, now after the collision, so this is upon the collision. Okay, after the collision, the two stick together, and you can imagine this guy with along with the party will have speed moving and then compressing the spring. Okay, so now it's going to compress the spring with the party there sticking together to a maximum compression. Let me call that as D. Okay, and then after the collision, so this happens after the collision. Okay, so there are actually two parts of the problem. The first part is on the collision, up on the collision. Okay, let me see. So we're looking for that D. D is what we are looking for, and we know that K is given as the spring constant. K is given as 24.0. Okay, and I think we have everything indicated over here. So we're looking for that D. Let me stop sharing so you guys might have a larger view on your side. If you click on speaker view, you should get a larger view now. So then upon the collision, because it's a collision problem, you can apply conservation of momentum. So conservation of momentum should apply. Okay. After the collision, you can see if you treat the block and the party as one system, now it's just pushing the spring, right? The surface is frictionless as indicated in the problem. So then there's only spring force doing work on the system. So spring force is a conservative force. So you can apply conservation of mechanical energy. So conservation of mechanical energy will apply. Okay, mechanical energy. So basically, we are going to look for the two parts of the problem. So we can look for the first part. Okay, upon collision, momentum conserved. So then you can do P initial equal to P final. Okay, initial momentum, it should be the small mass times the V0. That should equal to, now the two stick together, you should put the mass together, times the velocity after the collision. Okay, so this is before collision, this is after collision. You can solve for this V. Okay, so then V is again equal to mv0 divided by capital M plus small m, 0.0454 kg. This is small m plus 0.454 large, or sorry, that should go to the bottom. The combination of the two should go to the bottom. So V equals to 0.0454 kg times the V0, 8.80 meters per second, divided by combination of the two masses. Okay, that's going to give you 0.800 meters per second. Okay, so this is the speed, or the common speed after the collision for the two together. So then after the collision, conservation of mechanical energy is conserved. So you are going to apply the Ke initial, that should equal to Ke final, or Me, or just E, mechanical energy, sorry. It should be kinetic energy plus the potential energy. In this case, because there's a spring here, so then it's the elastic potential energy, okay? So right after the collision, the kinetic energy of the system, so this is like Ke plus U equals to initial equal to KE final plus U in final, okay? So KE initial is 1/2 the two combined V square. Potential energy initial, because it's at equilibrium point for the spring, so that's 0. Potential energy is 0 initially. And then equals to KE final. Now KE final, when the block and body is pushing the spring to a maximum compression, then the velocity final here should be 0, right? When the compression is maximum, velocity should be 0. So then kinetic energy should be 0, okay? Plus the potential energy in this time should be 1/2 K times D squared. Okay, so for potential energy of a spring is 1/2 K X squared. Now X is being the D, the maximum compression. Okay, so you're looking for the D here. So basically, this guy equals to that guy. You're looking for D. Okay, so let me write on this side. 1/2 capital M plus small m V squared is equal to 1/2 K D squared. Okay. So you can see 1/2 and 1/2 will cancel out. And then you can divide both sides by K to get rid of that K. So then you only have D squared remaining on the right hand side. So then take square root over K. Now you can put the V squared in under the square root, or you can put outside the square root. That means just V. Okay. That should equal to D. So take the square root of the left hand side should equal to the square root of the right hand side. All right. So then you can plug in all the numbers you have. So 0.0454 kilogram plus 0.454 kilogram divided by 24.0 newtons per meter, square root of it, times 0.8, yeah, 0.800 meters per second. Okay, that's your D. And that's going to be roughly 0.1154 meters or 0.115 in meters. Okay, that's your D. That's the maximum compression you would have for this guy. Okay. So on this one, you have, yeah, so you can divide the problem into two parts. The first part is upon collision, then conservation of momentum apply, and then the second one is after the collision. So there's only spring force here, so then you can apply conservation of mechanical energy. Okay, so this is one of the problem you have, the integrate concept. Okay, now since we have a few more minutes, let me just tell you that another problem you might be encountering involving the collision and in conservation of mechanical energy. So basically, you the second famous example is a pendulum system. Okay, so if there's a block hanging underneath a stream here, then that's capital M. Now it's well likely you are going to fire a bullet into the block here. So this guy will be small mass. Okay, and then so then upon the collision here again, upon collision, you can apply conservation of momentum. So P initial equal to P final. Okay, conservation of momentum. And then after the collision, if the bullet is embedded in the block over here, it's going to send this system up to a certain height. Okay, so the bullet is inside the block. And then the height over here, H, should be referring to the original position of the block and then the final. Okay, so in that case, now after collision, you are going to apply conservation of mechanical energy. That means Ki plus Ui equals to Kf plus Uf. Okay, in this case, the potential energy is going to be the gravitational potential energy. Okay, so you should be able to figure out the h over here, or maybe the h is given. If the h is given, then you're most likely looking for the initial velocity of the bullet. Okay, or the other way around, if the original velocity of bullets are given, then you'll be looking for the maximum height h. Okay, so two scenarios you might be asked for this type of question. Okay, but this is similar to the one we just checked. Okay, only the potential energy is in a different form. Okay, all right. So I think that will do it for today's lecture. Okay, so any questions you guys might have before I let you guys go? All right. If not, then I'll see Wednesday's lab attendees this afternoon. Okay, and then the Fridays on Friday. We will come back on for the lecture on Friday. Okay. If you are in quarantine for right now, don't worry. There's an opportunity for you guys to make up your missing labs. Okay. Otherwise, I'll see you guys in the lab. Okay. Bye.